All right, so let's take a look at another example. So shift to the whiteboard here. Let's look at so again, if we were evaluating acid and base behavior here, what we need to look for is where did the hydrogen go? So if I look at the bicarbonate ion and recognize that it went to carbonate, I can recognize that I lost a hydrogen along the way. That would be acidic behavior. The hydroxide, on the other hand, turned into water, which means it had to gain the hydrogen along the way. That's base behavior. So in this particular case, we'd be talking about the bicarbonate ion as an acid and the hydroxide ion as a base. Right. In this last example, we have now the bicarbonate ion reacting with ammonium ion to make carbonic acid and ammonia. We're going to do the same process. I look at the ammonium, it turned into ammonia, it lost the hydrogen along the way. That means it's an acid. Bicarbonate ion gained a hydrogen to become carbonic acid. That's basic behavior, adding a hydrogen. And so in this case, the bicarbonate's acting as a base, and the ammonium ion is acting as an acid. Now there's a vocabulary word in here that I want to see if you guys remember. What do we call a substance that can act as an acid in one circumstance, but as a base in a completely different circumstance? I know you know. Yeah. Amphiprotic. Okay. So for those of you in biology, like amphibian, dualistic, protic, proton, so it can act dualistically toward protons. It can gain them in certain circumstances, lose them in others. Bicarbonate ion is a good example of this. Water is a good example of this. So just a word to stash in your vocabulary. May not come up on Monday, but may come up in a future circumstance on that national final. Okay? What other things can we talk about? Oh, okay. Any specific kind of
molarity to molality.
okay, okay. Now, you're not going to be responsible for molarity to molality on this exam because, again, that molality is a chapter 11 concept. But molarity to mass percent, yes, we can do that. Okay, so on this particular question on the quiz, so question one where you were given, I would say more of you missed the question because you got the formula wrong of the substance that you're trying to find the molarity of than any other mistake. Many of you put it together correctly, but you had the wrong molar mass because you had the wrong formula because you didn't interpret the nomenclature correctly. So in this one, we need to start with what is calcium nitrate. Calcium nitrate, CaNO3 taken twice. Now, what we need to remember about percent is that we have a ready-made definition for it. 19.1 grams of calcium nitrate for every 100 grams of solution. By definition, that is what percent means. Grams per 100 grams. So really what we need to do here, to turn it into molarity, we need to turn this into moles of calcium nitrate over liters of solution. Now, there are lots of ways to approach this. And what I've kind of uncovered as I've talked to a number of you about this particular problem individually is that most of you hate the dimensional analysis method. So we're not going to show you the dimensional analysis method here. I think in that reason, it'll probably make this a little bit simpler as a result. And maybe lead to less confusion. So what we're going to do, since we're not going to do dimensional analysis, what we have to do is basically two series of calculations. One calculation converting the grams of calcium nitrate into moles, and a second calculation that turns the grams of solution into liters. We're going to handle them separately and then put them back together. So how do I turn grams into moles? That's right, it's the molar mass. So I need the molar mass of calcium nitrate. Calcium is 40.08. Nitrogen is 14.01, and there are two of them. Oxygen is 16, and there are 6 of them. 164.10 grams of calcium nitrate in every mole. So if I do 19.1 divided by 164.1. 3 sig figs, it's 0.116 moles of calcium nitrate. So that number of moles is going to go into the numerator of this fraction. Now I just need to do the same thing, converting the grams to the liters. 100 grams of solution. Here's where my density comes in. 1.03 grams of solution in every milliliter. Then I need to convert it into liters. 1,000 milliliters in a liter. 100 divided by 1.03 divided by 1,000. Again, to 3 sig figs is 0.0971 liters. So that number is going up here. So now I have my moles. Now I have my liters. I just need to divide the two. 0.116 divided by 0.0971. And I get 2 3 significant figures, 1.19 molar calcium nitrate. It's really, that's it. That's the process. Now, if we have to go the other way, kind of the same thing. We're just going to reverse it. We would start with the molarity, this many moles over 1 liter, and then we would convert the moles to grams and the liters of solution into grams of solution. We would divide the two by each other and then multiply by 100 to get it into percent. So basically, it's just this process going the other way. And then the last step, we have to multiply by 100 because we don't have 100 grams of solution. We're going to have whatever the number of grams is instead. All right. Any questions here? All right. What's something else that we want to talk about? I'm sorry. With dilutions? Okay. So let's take this 1.19 molar solution of calcium nitrate. And let's take 50 milliliters of it. And we're going to add 300 milliliters of water to it. How would we go about figuring out what the new concentration of our solution is? Okay, there is a formula that we use. Anybody know it off the top of their head? It's C1V1. That's right. C1V1 is equal to C2V2. So our C1 and our V1 are right here. This is what we're starting with. We have 1.19 molar and we have 50 milliliters. C2, we don't know the concentration. What is V2? Okay, what volume? What is it? It's more than the volume of water. Right. We're adding that much water to this much solution. So it's going to be the grand total of all the volume of this new solution. So it's not just 300, it's 350 milliliters. Now, one important note. Ordinarily, when we multiply molarity and volume together, we want that volume to be in liters because we want the liters to cancel out to give us moles. When we're using the dilution equation, we don't need to do that. And the reason we don't need to do that is because consistency. If I keep my unit of volume the same on both sides, when I go to do my algebra and divide each side here by 350 milliliters, those milliliters are going to cancel out anyway. It is that same logic that we can apply to using this dilution equation for other concentration units other than molarity. So if you watch the video I put out yesterday about problem number 4 in the osmotic pressure post-lecture, I talked about that very thing where you had to convert the percent into molarity at some point. You could choose to do it at the beginning, or you could choose to do the dilution equation first and then take that concentration and convert it at the end. And in the video, I did just that. I diluted it and then I converted it. So if we follow everything through, 1.19 multiplied by 50 divided by 350 to 3 significant figures. This would be 0.170 molar calcium nitrate. Now, in addition to problems like this, which are a little bit, this was a little bit straightforward. I kind of gave you the pieces and we just had to put them together. What if I gave you something more like this? How do you make 250 milliliters of 0.19 molar sodium hydroxide from 6 molar stock solution? Well, the answer is relatively straightforward. We're still using the dilution equation. What we need to make sure we get straight is what volume and what concentrations go together. You know, think about the titration equation problem that we did in that quiz. That was one of the bigger mistakes made, other than not balancing the equation and getting the correct mole-to-mole ratio. It was flip-flopping the volumes and putting the volume of acid with the concentration of base, or vice versa. So what two values go together? Okay, So I know I'm gonna put the concentrations on opposite sides of the equation, so let's just go ahead and do that. 0.19 molar over here. 6.0 molar over here. So I've taken care of this one. I've taken care of this one. Where does the 250 go? Okay, it is the final, but the way I set this up, this is the final concentration, right? The 250 needs to go with this concentration value. So yes, we ordinarily think of this as initial and final. But if we forget and we flip-flop them accidentally, it'll still work if we keep the pairs together. So what's important here is that the 0.19 and the 250 are on the same side of the equation. So you're right. Ordinarily, we think of the left side as initial and the right side as final. But if you forget, or if you accidentally flip-flop them, it's okay. What really matters is the molarity and the volume need to be together, describing the same solution. So that being said, 6 molar, divide each side to get rid of the molarity. .19 times 250 divided by 6, the two significant figures, is 7.9 milliliters. Okay, what does that 7.9 milliliters tell us? The 7.9 milliliters doesn't really answer the question. The question is, how do I make this particular solution? 7.9 milliliters is an important part of what we need to do. How do I finish it? It's as simple as writing a sentence. Measure 7.9 milliliters of the 6 molar stock solution and dilute to 250 milliliters. That's really what the question's asking. Question wanted to know, how do I make that particular solution? The dilution equation told me how much of the stock I needed. Well, if that's stock, the rest has to be water. So I just add water to get to that volume, whatever that volume may be. All right, what else can we work on? Sure. All right, let's jump away from the whiteboard here for a minute. Go back to the practice test. So in your practice test, this question is kind of almost exactly like that oxidation number proficiency that we've done. So let's kind of mimic that process to help out. So the first thing that we need to do is we need to assign oxidation numbers to everything here. And once we've assigned oxidation numbers, then we can go about the process of determining what was oxidized, what was reduced, what the oxidizing agent is, what the reducing agent is. Now, I will tell you, the easiest point on the exam on Monday is the answer to this question. You don't write yes, I'm gonna slap you. Because I wouldn't go through all this to pull the rug out from under you and make these all blank questions. Because if it's not redox, then there's no oxidizing agent, there's no reducing agent. That's the coolest trick question in the world. And I'm not that cool. But anyway, 3 points. No one in this room, no one watching on YouTube should miss this. But that being said, if we know that it is redox, then we better find a difference here between the reactants and products. They all come out as the same on both sides, then you know you made a mistake. All right, so let's go through this. So if I'm looking at the carbon monoxide, for carbon monoxide, we know that oxygen is -2, which means that the carbon has to be +2 to keep the carbon monoxide neutral. And for the hypochlorite ion, we know that the oxygen has to be -2. So that means that the chloride or the chlorine atom is going to be +1 to match that charge on the hypochlorite. On the flip side, we've got the carbonate ion. Now we could do the algebra here if we needed to. Carbon plus 3 oxygens equals -2. Since oxygen is -2, then I've got carbon -6 is equal to -2. So carbon must be +4. So +4 for the carbon, -2 for the oxygen. And now I've got chlorine here in a neutral molecule. So it has no charge. It's neutral itself. So on the easiest question on the test, the answer is yes. But now we have a good reason for it. We can look and see, okay, my carbon has changed in value, and my chlorine has changed in value. Specifically, carbon has gone from +2 to +4, which means it has lost 2 electrons. How would we describe the process going on inside of the carbon? Would this be oxidation or would this be reduction? It's oxidation. Loss of electrons is oxidation. So this is an oxidation process. On the other hand, the chlorine went from +1 to 0. To do that, you have to gain an electron. The gain of electrons is reduction. Now, that wasn't asked of us, but it's still important. So if you missed this particular item on the chapter 8 quiz, this is what you had to do. You had to assign oxidation numbers, and then we were looking specifically for elements that were changing, elements that were being oxidized or reduced. And so if you did something like said that the ClO minus was reduced, that isn't really correct. Part of it was the chlorine, but the whole ion was not. Where that whole ion comes in is when we identify the agents. So just like when we were looking at Bronsted-Lowry acid and base, oxidizing and reducing agents are on this half of the equation. They are reactants. So on the exam, that means that you're going to have a 50-50 shot if you do it right, because it's either going to be carbon monoxide or hypochlorite for each one. One of these is the oxidizing agent. One of these is the reducing agent. You just got to figure out which one's which. And the oxidizing agent is going to be the one that contains the element reduced. So that means that the oxidizing agent here is the hypochlorite. Hypochlorite ion, you know it better as the active ingredient in bleach. And so when you bleach something, you're doing a redox reaction to that thing that's causing it to decolorize. The reducing agent in this case would be what's left over, the carbon monoxide. Remember, the reducing agent contains the element that was oxidized, which in this case would be the carbon. Do we want to do another? Okay. So let's take a look at another here. Go. So for question number 23 here, we don't have to do the full breakdown, but let's do the full breakdown just for practice sake here. So I've got nitrogen dioxide reacting with ozone to make dinitrogen pentoxide and oxygen. What we want to know is what is the oxidizing agent in this reaction? Well, we got to do the same thing that we did on in the previous problem. Let's start with oxidation numbers. So let's split it down the middle. I've got nitrogen, I've got oxygen in NO2, and I've got oxygen in ozone. And on the flip side, I've got nitrogen, I've got oxygen in the dinitrogen pentoxide, and I've got the oxygen in O2. So to assign oxidation numbers, I need to look. So nitrogen plus 2 oxygens is equal to 0. Each oxygen is -2. So nitrogen plus -4 is equal to 0, which means that the nitrogen is +4. So I've got +4 for the nitrogen there. We've already established that the oxygen in it is -2. Now, what about the ozone? Yeah, even though this isn't the natural elemental state, it is still an allotrope of oxygen. It's a neutral molecule containing only oxygen atoms. So from that standpoint, every one of those atoms is chargeless. On the other hand, over here now, N2O5, 2 nitrogen plus 5 oxygen is equal to 0. Each one of these oxygens is -2. So I've got 2 nitrogen minus 10 is equal to 0. 2 nitrogen is equal to +10. So nitrogen is equal to +5. What's the state of oxygen in oxygen molecule? Still 0. So this one's kind of a tricky question, because we know it's redox because the nitrogen is changing state. And we know that we can't have an oxidation like that without a reduction happening somewhere. But what's confusing is, at least based on the state of these oxidation numbers, the oxygen doesn't look like it changes until you look a little closer. I had 3 oxygens in the ozone. Only 2 in this molecule. One of these oxygens jumped off of here and went over here. So from that standpoint, oxygen became a -2. And so oxygen in ozone was reduced. Nitrogen in the nitrogen dioxide was oxidized. Our oxidizing agent here is the ozone. Now, for problems like this in the multiple choice, remember that there's more than one definition of oxidation. And if you remember that this particular question is actually a lot easier. Most often we look at the track of electrons. But remember, one of the alternative definitions I gave you for redox was all about oxygen. Follow the oxygens. The oxidizing agent loses oxygen. The reducing agent gains oxygen. If I go from that standpoint and look close, the ozone has lost an oxygen to become oxygen. The nitrogen has gained oxygens to come N2O5. That alternative definition means we don't have to assign oxidation numbers. If oxygen is involved in the equation and we're dealing with multiple choice, that's all we need to look for. Just follow the oxygen. The oxygen will tell you what the oxidizing agent is. It'll tell you what the reducing agent is. It won't tell you what element is oxidized, but it'll give you an idea of where to look. Like in the problem above. In this reaction, which species is oxidized? Well, follow the oxygen. The copper gains oxygen in the form of the sulfate ion. A gain of oxygen means oxidation. The only thing that could have gained oxygen there is copper. Correct answer is A. Now you could solve this with numbers. Copper went from a 0 state to a +2. But again, I'm telling you this has to save you a little bit of time. Assigning oxidation numbers could take a while to do. If we're just being asked little bits of information that aren't oxidation number related, we can look for things like, where does the oxygen go to help us answer these kinds of little questions. And so long as we're not asked to do the whole thing, like in the short answer section, we can get away with a little bit more. We can cut a couple of corners to save ourselves time because it ultimately gives us the same answer anyway. For a question like number 21, there's no way around it. You gotta break it down, figure out what the oxidation state is that you're looking for. The only thing that you can kind of lean on a little bit is if you've done enough practice, you should recognize the hydrogen splits off. So what you're left with is the anion there. The anion here happens to be -1. So I'm looking for a +3, and oxygen's -2 each. I'm looking for the one that has 2 oxygens in it. All right, any other questions about redox? Or do we want to keep doing examples? We've got about a half hour. Isaac? Number 4 in the short answer, multiple choice. Okay, which compound below will exhibit hydrogen bonding with itself in the liquid state? Okay, so the key to this one is understanding that since we're dealing with organic molecules, hydrocarbons, carbon is going to be the source of the majority of those bonds. So what I mean by that is, if I'm looking at this formula, for example, I can clearly see that this oxygen is in the middle of those 2 carbons. So this isn't going to exhibit hydrogen bonding because I don't have an oxygen bonded to a hydrogen. I got oxygens in the middle of carbons, and the carbons are bonded to hydrogens. But the oxygen's not bonded to the hydrogen itself. Same thing for letter B. Same thing for letter D. And honestly, same thing for letter E. That fluorine there isn't bonded to the hydrogens, it's bonded to the carbon. Remember, carbon forms 4 single bonds. So we need to figure out kind of where it's going. For these kinds of questions about hydrogen bonding, what you need to look for specifically are NHs and OHs. Because the only fluorine compound that hydrogen bonds is plain old HF. Remember, fluorine, because of its electronic structure, only makes 1 bond. So if it bonds to a carbon compound, it's not going to bond to hydrogen as well. It's going to bond to the carbon or the oxygen or whatever. It only forms the 1 bond. So the only hydrogen bonding we get out of fluorine is in hydrogen fluoride. Everywhere else, we're looking for one of these groups, either a hydroxyl group like this or an amino group like this. So either NH or OH. That would indicate that we're dealing with an alcohol or an amine, and those would hydrogen bond. So C is the correct answer there. But otherwise, all 5 of those molecules are actually polar. And the way we look for, what we look for in terms of just general polarity, remember, we're looking for those elements of asymmetry. Oxygens in the middle of carbon compounds are going to cause those carbon compounds to bend. That's going to create that asymmetry. Other questions, other things we want to talk about? Okay. When an ion is dissolved in water, which intermolecular forces are in effect? Ion dipole, 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 and or London dispersion. The answer is all three, letter E. Why that? Well, remember, if a substance or a pair of substance exhibits high interactions, it's also going to exhibit the lower interactions as well. So the ion dipole forces are going to be between the ion itself and the hydrogen bonding in the water. Remember, to have ion dipole forces, you need to have ions and you need to have dipoles. The ions come from the ionic compound, the dipoles come from the water. The dipole forces will not be water to itself. And then the London dispersion forces, everything has London dispersion forces. Doesn't matter what it is. Everything that has electrons has London dispersion forces, because London dispersion forces are caused by the random motion of those electrons. So since we have all three, E's our answer. Correct. Because the only way that you make the ion dipole is you have to have something polar to connect to the ions. If I have something polar present, that polar thing is going to attract the other polar things in the solution. All right, what else can we talk about? Great. Okay, we can do one. Okay. But this practice test doesn't actually have a titration on it. We'll just make one up.
Is there any chapter 8?
In this? Yeah. The chapter 8 would be, this is the solution stoichiometry. So on this particular exam, I didn't do a titration. I did solution stoichiometry instead. But yeah, what you would have to do is you'd have to convert the milliliters, or in this case, the grams of copper into moles of nitric acid through stoichiometry, and then divide the moles by the liters to get the molarity. And then this one would, yeah, this one's just straight stoichiometry. And then this would be another chapter 8 problem here, the conversion. We did examples of that already this afternoon. All right, if this question looks familiar to you, it's because I just took it right off of the chapter 8 quiz. Change the numbers. So with a titration, again, the difference between a dilution and a titration is the fact that we've got a chemical reaction taking place. So even though the equations are similar, we have to keep that in mind. And probably the most consistent issue with this problem on the quiz was the lack of balanced chemical equations that we're showing. So because we didn't give you a balanced chemical equation, we wanted you to write one so that you could properly give us the correct ratios of each to each other. The active ingredient here is magnesium hydroxide. Now, if we go to the periodic table, magnesium's Mg, hydroxide we should know already is OH minus. Magnesium is an alkaline earth metal, it's in group 2, so it's got a +2 charge, which means that the chemical formula for magnesium hydroxide is going to be MgOH taking place. This is going to react with hydrochloric acid, and it is a double replacement. We're going to take the hydrogen and the magnesium, switch them around. So I end up with magnesium with its +2 charge and chloride with its -1 charge. So the correct formula for magnesium chloride is MgCl2. Wipe off the charges. And we've got hydrogen hydroxide, better known as water. To balance, I see that I have 2 chlorides over here, so I'm going to need 2 hydrochloric acids to give us the 2 chlorides. That leaves us with 2 hydrogens and 2 hydroxides, which would make 2 waters. So there's my balanced chemical equation. This was the thing that we were looking for on the quiz that a lot of you did not give us, and for that reason, you didn't get the right answer. Now that we have it, remember our titration equation. Molarity times volume for the acid over the acid's coefficient is equal to molarity times volume for the base over the base's coefficient. Subbing in what I know that the molarity of the acid is 0.15 molar. The volume is what I'm trying to find out. And the balanced chemical equation gives me a coefficient of 2 for the hydrochloric acid. On the other side, the molarity of the base, 1.117 molar. The volume, 25 milliliters. And the coefficient on the magnesium hydroxide is a 1. To solve, I'm going to need to multiply both sides of the equation by 2 and divide both sides of the equation by 0.15 molar. That'll get the 2's to cancel, the 0.15 molars to cancel over here. I'll be left with just the volume of acid. On this side, 2 over 0.15 molar. I'm going to get the molarities to cancel. And that's it. 1.17, or excuse me, 1.117 multiplied by 25, multiplied by 2, divided by 0.15, to 2 significant figures would be 370 milliliters of acid. So really, the key to these kinds of problems is we gotta make sure we have a balanced chemical equation. Without that balanced chemical equation, there's no way to get the correct answer unless we just luck into it, and it's a 1-to-1 ratio. And just like with the dilutions, making sure that we match up the correct values with each other. Again, the second most common mistake was flip-flopping either the volumes or the concentrations, having the wrong pairs with each other. And so that's where labeling can be really important, just kind of taking that second and circling, okay, this is for the acid, this is for the base. Just so that you have them straight when you go to move them into the equation. Right. Any other things that we want to talk about? We've got about 15, 20 minutes or so. No? Okay. Well, she did. Okay, so this is off of the practice test for Professor Lowe. This is similar to a chapter 7 quiz question. Now, for questions like this, there are a lot of different ways that you can approach it. You can approach it from a mass percent perspective. So one way to do it would be you could take the molar masses and basically set up a proportionality. 3 times 10 over the whole mass of the tin-4 phosphate is equal to 50 grams of tin over X. That's one way that you could do this. And it's not a bad approach. The downside to it, obviously, is that you've got that X in the denominator, so you're going to have to do a little bit of flipping around to isolate the X properly, but you could do it. The other way to do it would be to take it from a more stoichiometric approach and recognizing that you can go from grams of tin to moles of tin, and using the chemical formula, go from moles of tin to moles of the product, and then use the molar mass to take it to grams. So let's look at each approach. So we'll start with the approach in black. That's the stoichiometry kind of dimensional analysis approach. And then I'll show you what some of you might think is the shortcut using the max percent. Again, it doesn't really matter. What matters is you get the answer right. So if we go from this kind of standpoint, 50 grams of tin Molar mass of tin, tin is element number 50, 118.71 grams in a mole. To get the moles of the compound, we need to use the formula. There are 3 tins in every tin 4 phosphate. And then finally, we need to turn that mole of tin 4 phosphate into grams. And this one's more of the labor of love because this is a big compound. It's going to have a large mass. 118.71 times 3 for tin, 30.97 times 4 for phosphorus, 16 times 16 for oxygen. The molar mass of tin 4 phosphate is an obscenely ridiculous 736.01 grams per mole. But if I do the calculation, everything cancels but the grams. 50 times 736.01 divided by 118.71 divided by 3 to 4 significant figures would be 103.3 grams of tin 4 phosphate. Now, like I said, that's one approach. The other approach would be using proportionality, because really this is just a mass percent question. So if I took it from a mass percent kind of perspective, molar mass of tin, as we established already, is 118.71 grams. And we already calculated that the molar mass of the compound is 736.01. Now, like I said, the issue that you're going to run into in this one in particular is because that X is in the denominator, algebraically, it's going to be more difficult to work with. Easiest thing to do to get rid of that scenario is to flip it. If I flip both sides of the equation, I'll get 736.01 grams over 3 times 118.71, which is 356.13 grams. And that is equal to X over 50 grams of tin. And so now, since the X is in the numerator, I just need to multiply both sides by the 50 grams. And if I do that, 50 times 736.01 divided by 356.13, I get the same 103.3 grams. So again, it's really about what makes most sense to you. One of the reasons I avoided the proportionalities when we taught this the first go around, a lot of people aren't comfortable with them from an algebraic standpoint. And especially if we get that variable in the denominator, a lot of mistakes get made. I've tended to focus on this method, even though it might be a little bit more rigorous, just because it's always easy to see those units canceling out as you go step to step to step. Again, what you do with the information is completely up to you. Do what you feel most comfortable with. All right, I think we've got time for one more question if we have it. All right, sounds like we're okay. Thanks for coming out. I will be available on the weekend. If you do have a question, send me a message to remind. I'll try to I won't get back to you immediately. I will get back to you. See you on Monday. Have a good weekend.